this kind of webinar is a little bit special. We don't really look into how to use our software, but it's a more broader understanding of how the software actually works. When it comes to structural calculation, I think it believes it's more important to understand first where are the limits, how does it work, before really diving into using it. So this webinar series was basically created from the feedback that we got with LDI. So there were a lot of questions is, how does this actually work? We are not really able to trust the calculation. Where are the hand table calculations with this? And basically, this is what we want to have a look on to this webinar, is to give you a broader understanding of how FEA calculation actually works, what you're seeing in production assists, what is the limitation will of all of this, and how accurate are basically all the calculations with this. I don't think it's so, I tried to speak slower than last time. This was also feedback that we were getting, is that at some point we were a little bit in a hurry. So this time I'm trying to make it a little bit more slow and explain it a little bit better on what's going on and how it works and stuff like this, so that we actually, that's actually understandable with this. So now it's 30. With this, I think we can actually start with it. So the first thing that we will have a look today is the convention and what you actually will see when you're using production assist in here. The first thing in here that is really important with all the calculation and stuff with this is to basically understand the coordinate system. So the coordinate system is a coordinate system which is in relation to the truss. And for all of the applications for production assist, the coordinate system in which all the calculation results are expressed are always in line with the truss. So the x-axis from our coordinate system is always running in the direction of the truss. The y-axis is always moving to the side, and the z-axis is always moving up. For our understanding and for our truss, the direction of the z and y-axis are always in line with the symmetry axis of the trusses. For most of the trusses that we have in production assist, this is true. So they are symmetrical, and then the z-axis is always aligned with them in such a way. Another thing that you see in here in this example is that the z-axis and the x-axis actually can be tilted in correlation with the global coordinate system in here. So this basically means the z-axis is not always pointing up, but it's always locally defined by each truss piece in here. So all of these values that we are seeing, you always find in the calculation results object. So it's this blue object, so it's this object entry with a small calculator to the left, which is called calculation results. And when you see in there, there are a lot of like influence lines, which are in the object info properties from this. And we will dive a little into this to actually understand what they're meaning for and how to use them. The first one that we have is basically the deflections that you will see. The nice thing about the deflection is that it's actually really easy to see and to understand with this, and it's a good example to get started with it. In Production Assist, we display 4 deflections. All of them are always colored in blue. The first deflection that we are seeing in here is the deflection DZ, which is the deflection which is happening into relation the local z-axis of the truss. Then we have, so this is what you see to the bottom right with this, so the big blue line. Then you have the deflection DY. The deflection DY in this case goes to the side, but is also a little bit tilted and basically means that the truss is a little bit tilted to the side with this. The other deflection, dx, is a deflection in direction of the truss. So this basically tells if a truss gets longer or smaller because of the compression in here. In this case, it's most likely to see this with the hoists in there. So as you're hanging something in the hoist, actually they get the chains that they have get enlarged a little bit, and that is what is also displayed. All the things that we are showing in here are called vectors. A vector is a value that has a specific direction. So in this case, the vectoral force, the vectoral deflection that we have in here is called du and is the line that you see onto the bottom, which actually is pointing down. So in this example that you're seeing in here, actually you have a truss which is tilted around the z-axis and also a little bit rotated around its own axis. So for the calculation, this makes actually a big impact because now all the values that you get out of it are also a little bit tilted with this. So for the deflection, normally it's not so important to look onto dx, dy, and dz. It's more easy to look onto the du deflection with this, which is just basically the combined deflection of all of this. So basically what's happened if you add dx, dy, and dz in there. When doing the structural calculations, from our experience, every user can understand the deflection figure real easy, because they just have a natural understanding of how deflection for any given structure should look like. You have it in your feelings because you're looking on all the structures all the times, and you see that's how it should deflect in there. And that's a really good way to actually check if the calculation that you're doing is good or not. For example, if you have very big deflections and maybe some truss pieces are not lining up, that's an indication for that they are not connected with this. So the check of the deflection figure is really something that makes it simple for you to understand what's going on. The other thing that we have in here are so-called shear forces. Shear forces are the green lines that are displayed in Production Assist. There are two of them, the shear force Vy and Vz. Vy goes to the right of the truss. So it's basically the shear force that pulls the truss apart from each other, while the shear force Vz is actually pulling it in such a way. The force in here is also is an alignment to a mass across the acceleration. So actually what you have in here is that every fixture or every object, every rigging load and stuff like this has a mass, and the acceleration of the Earth, so the Earth's acceleration, pushes them down. That is generating the force. The force is also a different vector in here with this. So in this case, basically the vectoral force from the lightning device, which you're seeing in there, is pointing directly down. But because the truss is a little bit tilted, these forces need to be recalculated for the rake truss. So part of its weight goes into Vz, in this case the majority of the weight because the line is longer, and Vy takes the other part of it. If you would do a vectoral addition for Vy and Vz, they would directly point down with this. Shear forces, when you see them in your calculation, normally create pressure or tension in the bracings of a truss. So they do not really go into the main tubes, but into the bracings. So when doing calculations with this, the shear force is normally really big when you have short trusses with a big load. So typically, when you're doing pre-rig calculations, the shear force is a thing that actually limits the capacity of the truss in here. The other force, you can ask questions if you want with this. And then we cut it just out in the next time. The next thing that we have is so-called normal forces. Normal forces are pretty similar like the shear forces, but they go directly into the direction of the truss or the hoist. So typically these normal forces appear on raked structures. So when you look on the truss in here, you see it's also a little bit raked. So part of the truss is pulled and part of the truss is actually pushed. That is also in ground supports where you have columns. This can happen with the normal forces. In production assist, they're always colored in light blue and are always into relation to the cross section like this. Most of the times, if you're calculating hanging systems, you will see them on hoist with this. If you have a normal truss, if you have a normal force inside the calculation, typically they create pressure or tension in the tubes of the truss, but don't go into the bracings. The most important part for most of the calculation is the moment. The moment is a force pair, so basically a force that has a specific lever to a supporting point with this. A moment is also have a vector. So it's also aligned to this coordinate system that I was talking before. There are two bending moments. One is called MBY, which is bending around the y-axis. And then there is MBZ, which is bending about the x-axis. So basically bending moment MBY pushes my truss down, while the bending moment MBY is pushing it to the side. So when you're having ground supports calculation, it's typical normal to see both of those values. If you're having just the hanging structures, as long as the trusses are not raked, the bending moment MBY is normally the only bending moment that you see. Bending moments create pressure and tension in the tubes of a truss. And if you have longer span width of truss, normally this is what is limiting the actual capacity of the truss in here. An important thing to understand is that it's not good enough to just compare the bending moment with the maximum bending moment of the truss, because the bending moment MBY and the MBZ needs to be added into a specific point, and also the normal forces that are happening on the truss. So if you're having a little bit different raked structures, you need to take in all of those values into account. If you're using production assist, this is what is done automatically by all of these things in here and just works for you. The other thing that we have is something that we call torsional moments. Torsional moments happen if you actually twist a truss. So twisting a truss happens if you have a rigid frame and putting on lights on the different chords of the truss. So each of these things have a small lever against the middle point of the truss and creating this bending moment in here. Normally, the most bending moments you get out of outrigged structures when you outrig something with a pipe in here. So in this case, in order to make it really like visible with this, I've moved a really, really big load onto a lever so that you're seeing the bending moment, the torsional moment. The torsional moment also will be shown in light green. Depending on the type of the truss, let me just quickly try to move with this. Yeah, perfect. So now he's muted. Sorry for the disturbance. So depending on the structure of the truss, the bending at the torsional moment either only creates forces in the bracings, or it also creates forces on the tubes and the bracings. So for this, there's a really simple rule. So the nice thing is that my camera should now follow me, well, a little bit. So we have a truss in here. And when you look on this truss, it has a specific webbing pattern. So if you have the webbing pattern where at one part, all the four bracings go into one joint, then the truss only generates forces in the bracings for torsional moments. If you have this offsetted so that there is one of the two cords in here and one of the bracings in here, then actually it also creates typical forces in the cords and the bracings. A typical example for this in the European truss is Prolite H30V, which has this pattern that only generates forces in the bracings. And a typical example for the other part, so where it's also generating forces in the tubes and the bracing, is FD33 with this. So they are not really interchangeable, especially when it comes to this kind of torsional moments in here. This is basically the things that you're seeing on the truss in here and used to calculate the workflow, the workload. Production Assist has one special thing. Wait, that was one too fast. Sorry. Production Assist has one special check in there that needs to be done for trusses in order to check if they're still able in calculating the load and not. In here, you're seeing the joints of two trusses of a spigoted truss, and the yellow part is basically the connector. So during the part of the truss of the two connectors there is no internal webbing in there. So basically the rules of the webbing do not apply to this section. So in here, you need to do a special calculation in order to check that the truss at this part is not overloaded. This is something that Production Assist is just doing out of the box with this. So every truss which has this option in there automatically will be calculated with interaction. Interaction is a little bit challenging with this because it's not a linear thing with this. So depending on shear force and bending moment at this position, you get multiple values for this. So the impact on the workload of interaction could be between like 2% up to 20 and even up to 30%, depending on the actual use of the truss. So you really need to check each of the different connectors in order to make a difference in there. That's a little bit the things that actually Production Assist is calculating with you and what you're seeing in here and what you can turn on and off with this. The next thing that we actually want to have a look on is look onto the plausibility of the calculations that we have. For this, we start with a really, really easy system. So with a hoist system with two hoists in here and the dead load of the truss as only load in here. So what you're seeing, you have left and right the forces that go into the roof or into the hoist, which are the same with this. And you see green is the line load, which is applied to it, which is constantly changing over the truss with this. So that is basically pretty easy with this. Now we come a little bit into the math part of this thing in here. Don't worry. So all the calculations, all that stuff that we're doing, I explain a little bit with this, and you don't need to solve them on your own. So in order to calculate the reaction forces in here with this thing, you can use the sum of force and sum of moments around a specific point. This is something that you basically learn when you're becoming a rigger. So you're calculating how to you learn how to calculate forces onto two hoist system in here. So the sum of the moments around one of the support points needs to be 0. So which basically means that the one of the support forces with the lever arm of the length of the truss and the resulting force with the lever arm of half of the truss, the line load equals 0. And if you're then calculating this and solving the equation with this, it's really easy. You see that FB equals FA, and both of them take half of the total load which is applied to the system. This is something where we do in hands-on with this in order to jump into the first thing in here. So I have the exact same system in here that we also have with the other parts with this. I just make this a little bit larger. And we see that it's really 50% to the left and 50% to the right. So the interesting question that we now are asking ourselves is, what happens if we move up this hoist a little bit? So for this, I go onto the support, click onto the supporting properties of the first hoist, and go to the chain shorten in here. The chain shorten is a value that tells you how much the chain is moved up or down in the calculations with this. This is an option to actually look for unleveled truss and what kind of an impact it does have. If I'm now moving up in here, this kind of thing, you see when you move up the truss in here, actually it does not have any impact on the loads in here that you have for the calculations with these kind of things, which is pretty neat because this basically means if you have only two supports, depending on how the truss is running, it doesn't really make a difference in the calculation. There is one limitation to this system, which I want to point out is this only is true if the supporting legs of the hoist, so basically the chains, are keeping in parallel. So as long as this is the case, it does not change the load on the individual hoists in here. Now let's move a little bit more forward with this. So what we have in here basically is a hoist system with a truss system with 3 hoists in here. So normally what we hear when we ask how people are actually doing this and thinking how the load is distributing in here, they tell like 20% each goes into the outer point and about 60% go into the middle one. There are even more accurate numbers with this. We don't think that's a good idea to say it's like 62% and something into the middle, because this implies an accuracy that actually is not into the in the actual calculation in here. So let's have a look on the mass of this first. The first thing that we actually need to check in here is again the sum of the forces and some of the moments in here. So we don't really want to solve this, but the thing that we see in here is basically we have 2 unknown values, 3 unknown values in here. So the force on the 1, the force on the 2, and the force on the 3. And we only have 2 equations with this. So now it becomes a little bit into high school math with this. So if you have 3 unknown values and only 2 equations, then you can't solve it. So that's a limitation just by math that you have. So basically the normal rigging math that you have doesn't allow to solve you this. So now it becomes a little bit more challenging with this. So in order on how to calculate actually the forces onto this thing, we need to make it more complicated. So I was doing a lot of tutorials during my studies, and normally, so that's where you sit together with students and help them learn. And normally, if you put in the integral sign like this in here, all of them always know, oh, well, now I don't need to listen and just can sleep with this. Good thing we are not in university here, so it's more about explaining in there. How do we actually come to results in here? So the equation that we're going to use is this one. So basically there's a relation between the deflection of the truss and the loading of the truss, which is, if you think, pretty obvious. So if you load a truss more, it actually deflects more. And the link between is that there is the integral of it. So the rule is that the negative function of the load of the load of the truss, which is minus Q in here, equals the deflection at a specific position with this. Now let's have a look on the terms in here. A and I are properties of the truss in here that currently is not important for us. So that is basically how stiff a truss is. W from X basically is just a function that we tell defines a deflection over the truss run. So at 1, at 2, at 3 meters, basically. The integrals are basically some kind of magic. We don't want to dive too much into it. So just consider as at magic with this. So that's the rule how they are linked together. And minus Q is actually the load of the truss, which again is pretty obvious. The load of the truss and its deflection need to have something to do together. So with the magic of integrals, basically what we can do is we can calculate this. So if you resolve the integrals, you come something in there which looks like this. Unfortunately, you cut out two functions here. So one from the left to the middle and one from the middle to the right, basically. And you see now you have 8 unknown values, which are called C1, C2, C3, C4. Now, basically, in order to make our problem solvable, first we needed to make it more complicated. So why are we doing this in here? So the important part in here, now in order to solve this equation, we need to set so-called assumptions. So basically what we do is we assume a specific property of our calculation on a specific point. All the calculations or all the assumptions that are needed for this calculation are listed down in this table. We currently will only have a look on W at the point 0 equals 0, which is basically another word for at the start of the truss, so where the hoist is, there is no deflection with this. There's a chat message. Let me have a look. Equation, not equation. Equation. Thank you very much, Simon, with this. I'm sorry with this. That's my not native English speaking tongue with this. Let's move on how we actually do this with this. Click. So we've used the assumption that the deflection at the point 0 should be 0. So basically what we do is we set X equals 0. We see that basically when we're checking our calculation in here, this assumption is met. So there is no deflection at the position of the start. And then we basically just set X equals 0. If we do this, the same equation now looks like this. And the good thing, now the calculation is really easy and you don't need to think much. So if you look on the first part of the truss, minus Q cross O equal for cross 4, this becomes 0. This becomes 0. This becomes 0. This becomes 0. And then in the end, only there is C4 equals 0. And that is basically how you calculate such a system. You're setting up specific assumption about the property of the truss in here and how this can be actually used for calculation. There is one important thing in here to know if you don't meet these assumptions. So if the deflection at the point 0 is not 0, so if the truss is not leveled, it does not came out the same equation. So the important part to understand with all calculation with 3 or more hoists for truss lines or 4 and more hoists for any frame structure is that the actual result of the calculation depends on the actual assumptions that you do upfront with the calculation. Now we will have a look onto this and how this actually is managed in production assist in here with this. So we have a 3 hoist system in here. Wait, I think I need to close it before because I created from the same thing. Perfect. Okay, I didn't. Sorry for this. I did this right in here. So let me quickly add the hoist in here that we have our 3-leg system in here with this. So this is already right. Show the forces. cut down this to 2 meters, I think, something like this. So same thing that we're seeing in here with this kind of thing in here is this. So 0.3 kilonewton about go into the left and 0.9 kilonewton go into the middle. In other words, there's almost a little bit more than 3 times the load into the middle than into the side with this. So this is what we actually would expect with our calculation in here. So now if you're going into here and using the chain shorten and moving this up, you actually will see it changes the calculation result. So before it was 0.27, now it's 0.3. And now every time basically you click in here, you see that you're transferring load from the middle hoist to the other hoists in here. And well, as you could imagine, if you move it up enough with this, actually the load that is in the middle will go down to 0. So that's actually not taken in there. So in this case in here, what you will see, depending on the actual leveling on the truss, you can really distribute the loads from the left to the right and the other way around. Same thing in here when I'm now resetting this and moving up the middle hoist a little bit, I will take out load from the left points and move it to the other points in here. This is something that you discover, especially, for example, when rigging LED screens. There are really a lot of different grabs on the actual truss, and it really changes every time when you level it a little bit. The main problem in here that this kind of calculation effect that you're seeing has nothing to do with production assist or FEA calculation in general. It's just a property of any calculation with this. The reason for this, while the actual forces on the truss are dependent on this, are in the mass before, because you need to adopt to specific assumptions in order to do this. So every time you're getting a structural calculation from an engineer, if you're doing them by yourself or stuff like this, basically you're doing these assumptions. And if you don't match these assumptions, actually you will not basically reproduce your structural calculation with this. So in the practice, there are multiple ways of now handling this. The first one is actually to level your grid. So there is actually a need to level your grid so that the assumptions are met. The other one is actually to not to use load measurement cells. So basically, when you're running a structural calculation for a big grid, you don't know. You only know that there is one way that you can hang it with these forces, and you use a load measurement cell to actually reproduce this kind of calculations in here with this. Production Assist has several features that help you a little bit understanding the process in here. So the most important one with this is, for example, the calculate effect from chain shorten in here. And this calculate effect from chain shorten basically does a calculation for all of the hoists in here and checks what is happening if you, wait, I think it's not allowed to have something selected with this. And calculate effect from chain shorten with this basically checks you for each of the calculation what's happening if you're moving the hoist a little bit up. So how much does the load changes, and gives you an indication on the actual workload changes of this. This is a really simple system with not much that can change in here. That's why you're not seeing that much with this. After the webinar, I show you a little bit with one of the drawings that we have what kind of effect to expect in here. Let's move on with this. The next thing that we will have a look on is really a little bit about the FEA calculations with this. The challenging part with the FEA calculations is that it's like kind of magic. So if you're doing the hand calculation with this, what you have is really like a table, where are the loads and stuff like this, and how this is done. I show you a little bit how this works with the FEA calculations. The main idea behind of this is that you actually get an understanding on what you actually seeing and what is happening in the background and why it's so hard to put this into tables with this that are human readable. So the first thing that we will have basically is an understanding of what kind of systems we have. So we use in 2D frame FEA element in here. So for production assist, obviously it's using a 3D frame element, but it's more easy to explain with a 2D element. So this 2D element had at each of the start and end points a force which is pointing up and a moment which is positive defined. And also on the left. Also, each of the pieces have kind of a deflection with there. So they can be pulled up or couldn't be put down, and it could be pulled up and down also on the other side with this kind of thing. The first part of our equation we need out of this is the actual stiffness of the system. So what we do is that for each of the different moments and forces, there's a relation between the forces that you apply in there. You don't need to look onto the values in there, but you just need to know basically somehow we are calculating the stiffness of the system using the specific rules for each of the internal 2D FEA elements. Basically, each truss becomes a 2D frame FEA element in here with this. The stiffness of this is depending on how the trusses are connected and stuff like this. And basically for every truss, we create a table that contains such values in here and use for calculation. The next thing that we need to know is the forces on the end and starting point of the trusses in here. So what we do, there are specific tables that define how the forces and moments transfer from the middle to the left and to the right. I've put you the most basic formulas as well in here. Again, we don't really care about the individual numbers which are in there, just on the process in here. So part of what this production assist is doing is basically for every load that you're applying somewhere on the structure, it looks up into a table and calculates when this load is in the middle of the truss, what does it impact on the start and ending point of the truss in there. There are specific rule sets on how to do this in here. The last part is putting it basically all together. So all of this, each individual small 2D FEA elements will be added together. And what you immediately will see that the deflection on the start and of the end of truss 1 equals the deflection of the start of truss 2. So basically they are the same and they are interconnected with this. So the equation that we now need to solve is K, which is the stiffness of the system, which has been built up from the trusses and how they are connected to each other, cross the deflection of the points. This is the actual unknown value in here. And these needs to be the forces of the nodal points that we have. And there's again a known value. So in this equation, K, the stiffness system of the stiffness of the system is a known value. F is a known value in here. And U is an unknown value. The nice thing is now for every unknown value, we have at least one equation in order to do this. We can solve it. The way how this works then is using matrices. So basically what it does is for each of the different deflections in each direction, it is calculating it against the stiffness. So basically the values that you have in here is always defining what is the relation between the different deflection and the forces in here. That's a normal linear algebra system with this that you can solve. That is something that you would learn in the school. And then you get the results. The interesting part of this is actually you're not calculating forces or reaction forces with the FEA calculation method that we are using, but the actual resulting deflections that this kind of system is actually making in here. So the important part in here that you need to know about this is that basically all the tables that you know for your hand calculation are part in the nodal force vector in here. So production assist calculates for every load, basically how this is added to the left and to the right load with this. The thing that is missing in your hand calculation, because it's not needed, is the calculation of the stiffness system. These kind of tables that are used, or these kind of matrices that are used for the calculation, can become quite big. So for the 3D beam elements that we're using in Production Assist, basically for each point, we have 6 values in there, which means if you have a system with 1,000 points that are connected with each other, we need to have a matrix by 6,000 by 6,000. So it has 6,000 equations with 6,000 unknown values, and that is what is calculating. Printing them out on paper would just take forever. So in this case, the trick that we're doing with FEA calculation, and which is all the other FEA tools also on the market is doing, is they just list all the loads on all the trusses and all the nodes that go into the calculation, so that you don't document the way how you get to the results, but you document the input parameters and you document the output values that you get out of it. And with this, you can just reproduce it with all the things. So all of this calculation, which are basically done inside the FEA core, are pretty much the same that you're doing on the hand, but a little bit more generalized with this, and a lot of them more. So basically, if you think about 6,000 trusses that you have in there, it's 6,000 equation. That sums up quite a lot. So it's a lot of multiplications that need to be done in order to solve this in here. Lucky you, that's the only part that we wanted to show about the FEA calculation to give you some impact with this. An interesting part a little bit with this, where we also want to have a look on this, because that's really a special thing of the Production Assist, is how we now calculate this with this. And the thing that we want to have a look on is the internal webbing calculation with this. The internal webbing calculation basically is the comparison between these two calculation schemes in here. So on the left, you're seeing that all of the tubes and bracings of the truss, they have been minified to one line of 3D beam properties with this. So that is a thing that works really, really well on the actual trusses with this. The main advantage while we're doing this is that it's way more efficient to calculate one element for this truss than calculate 500. So if you would use more elements to represent this beam, you would just bump up how much calculations you actually need to do this kind of things. So that's why in Production Assist, by default, we are using the center line structure to calculate it. This actually works very well for any type of straight truss and also curved truss, but it doesn't work very well at all for the corners in here, especially if the corners are really loaded. So a typical thing for this is ground supports in here. So when it comes to ground support, Production Assist has the ability to actually calculate the trusses using each internal member in here. So for example, it models all the bracings and all the tubes and actually allows you to calculate this. I've prepared an example for this that actually shows you the difference in here with this. So let me move in here. There's a corner internal webbing thing that I need to do with this. And in here, I just disable real quick the internal beam so that you don't see this. Show structure, press OK in here. So you're seeing it in here with this. So the important part that we are currently caring about is the so-called corner moment, or with this, which is on the end, and the so-called field moment, which is in here. So currently this calculation is actually set that the truss is, or that the corner is calculated with each of its internal structures in here with this. There is a setting in here that we've used where we actually can disable the use of the internal webbing with this. So I've done this in the other load case in here, which is just called Oracle Ultimate Failure No Corners. And if I'm changing this, you actually will see that also the calculation is changing. The important parts that we want to look on first is the actual field moment. Before it was 18.3, and if I would enable the corners, it would bump up to 21.68. So it increases a little bit. The important thing to know is that the maximum bending moment for this truss is 24. So 18.3 kilonewton meters is basically 80% of the workload. While if you actually putting in the corners, the truss actually would bear more load and would give you different calculation results in here. But that's not all with this. So if you would calculate this just with the normal truss cross section and don't care about the corner, you actually would think that the truss is at 79% workload. So that seems to be reasonable and seems to be a good thing to actually, would be actually a good thing to build. If you do the exact same thing with the actual trusses in here, you see immediately it jumps to over 100% in here. And if I'm now going into here and actually toning on the workload with this, you see you're at 600% workload with this. There's one thing to say about this kind of calculations in here with this. So this is a little bit, it's a little bit rigged, this calculation. So we have a really long span width and we have a really big force into the middle with this. So that's why it's this overloaded in here. But even if I'm deleting this middle load in here, we're still at 84% workload with this. So there is not much capacity in here. So an important thing to remember is if you have these kind of corner elements, they really don't take a lot of forces when not used in a laying way. So typical thing that we need to check with the ground support calculation is actually the corner elements, if they take up the force and if they work like this in here, and if you can use it. If you overload the corners, normally they don't really break first, but they will deflect a lot and they will actually change their way and their looking. So basically the 90-degree corner, if you load it this much, will not be a 90-degree corner after you actually use this. So that's an important thing to actually understand and to know with these kind of setting. An interesting thing about this is it does not really matter if you do this in the normal calculation things for the laying hanging truss structures. So as long as there's not much bending moment onto the corners and not that much shear force, they are normally loaded really fine with this kind of things in here. And that's normally not a problem, but it's definitely worth checking if you have like some special corners in there with this. Let's move on to the last thing in here, and then we are almost done with our webinar with this, which is the VDE 6201, which is basically a document in there which tells you what are the requirements for software-based structural analysis in here. That is a VDE document. So this is from Germany, and it's only, well, really like law in Germany in here. And it defines basically two parts of requirements in here. So one requirement, which is pretty obvious, is for the manufacturer. So as the manufacturer of the software in there, it gives us specific rule sets that we need to apply in order to make a VDE compliant calculation software for the users. The other thing, which is maybe a little bit surprising, it also puts a lot of requirements on the actual users with this. So it tells what do users need to do and to which standards they need to comply in order to use this. Maybe let's start with the easy part for you and the challenging part for us. The first thing that we need to give you is a documentation for our software with this, which is what we do on our webpage. So there's a definition on how to use the software, how to do it. We tell you about what are the limits and stuff like this. And we tell you how it works and what is the base fundamental models, which is basically the next step, which is also a requirement by VDE. That's why we're doing this webinar in here, so that we have also like a more vocal experience of this, so that you can, it's more easy learning curve with this. We need to give you some sample of the users, which you can download for this. We need to have an internal quality assurance. For example, here at Dearsoft, this is done by a lot of site calculations with this. So every change that we're doing on our software, we actually have unit tests that look, do they not change the actual calculation results? And if they change them, is this a good change or a bad change with this? It's also that we do a lot of comparison calculations with this. So we have different other FEA software in there, and then we check what does our software say the values are and what does the other software say the values are with this. And if they're the same or almost the same, that's a good sign. If they are not the same, then we need to dig into this. That is basically what we do every release and every day in order to check that we are not introducing any bad calculation in here. We need to offer you bug tracking and reporting. We need to open this to everyone. So we should not only people that are actually customers to allow them to insert bugs, but also all of them. That's why we have the support at Production Assist, that everybody can write in there if they find something odd with this. We need to train our developers quite a lot. So all of our developers which are working on the structural part are engineers, at least with a bachelor degree and 4 years of experience with this before they actually can touch things alone with this. They run through a specific training about FEA software and stuff like this, and how to use it, what are the limitations. So basically just the normal engineering stuff. And well, you need a help desk for the users, which in our case is actually the website chat with this. Which is also interesting what basically the VDE is telling you with this for the calculation systems in here. So the VDE definitely tells that you need to have the education as an engineer with this. So they also say you need to have at least a bachelor degree to come in there with this. You need to have training for this. That's the reason why if you're buying a license for us, we immediately offer you training with this so that you can do it and actually know what you're doing and stuff like this, and continue in education. So that's why we're doing the webinar program, so that you can actually learn. That's why we upload stuff to YouTube, that you actually can certify yourself in order to apply with the VDE norms with this. One important note that you need to know is that all the liability for the calculations always lies with the user that is actually doing it. So even if Production Assist would completely give you wrong numbers and it's really just the calculation software which is messed up, you did everything wrong, the VDE states that the end that you are in charge of actually checking the calculation results yourself with this. So this is kind of surprising with this, but really comes from we can't really know what you are doing with the software as a software developer and if it's a proper use with this. So that's why we have now added the service as a structural engineering service to Production Assist. So if you don't want to take over the liability for the calculation, you can table the calculation for our in-house engineering team. And basically, within 3 hours after you table this and there is nothing to discuss, they actually will certify your structural calculation, send you a STEM calculation report, and take over the liability of the calculations for you with this. So especially if well, there's a big liability issue for you or is something complex in there, it's really helpful to use the service that we are offering in order to get it away from your own personal liability in there.